Hi everyone. So we are going to continue with our fixed point lecture. And today I'll start with two examples, and it's intentional because before telling you like, oh, multiply this, round this, or, giving you an algorithm to follow or memorize a bunch of steps, I want you to understand what you're doing and why you're doing them, okay? Then if you download the second part of the fixed point, you'd see that I put everything on steps just to clarify that, okay? So first thing first, pen. Okay, first thing first, we are going to do, it says we have two numbers in Q7.8. One of them is in hex 5F80, the other one is 4100, okay? So first thing I want to tell you is that in your exams, in your assignments, we will always tell you that the first number that appears here, M, if it includes sign or not, okay? But as a rule of thumb, remember that if you add them up, okay? If you add M and N here, and you're only like one number less than the standard sizes, like 8 bits, 16 bits, 32 bits, then that means that this doesn't include the sign. You see? Like for example, 7 plus 8 here is 15 bits, right? So you're free to assume that, the sign bit is not explicitly included here. So this is basically, if you wanted to explicitly say the number of the bit sign, it should be equal to Q8.8. Okay, I'm just saying that because interchangeably you see, like especially with these standard sizes, you see Q1.15, 0.15, or like 2.30 or like 1.30. You would see these ones. With the with the ones that are non-standard, then you have to know if M includes a sign or not. For now, this representation means that we have 1 sign bit, 7 integer bits, and 8 fractional bits. Okay? This is the meaning of this one. Now, let's do this calculation. I already put them here so we have more space. The first number in hex is 5F80. Let's convert that to binary, okay? So I'm going to put this in the binary format. And through this lecture, I'll show you the hex, the binary, the decimal, and the integer. So this is the binary. And then, so in binary, 5 would look like this, F would look like this, 8, 0, 0, 0. For this one, it's like that, and then 1. So hex, every bit in hex turns to 4 bits. Every digit in hex turns to 4 bits in binary, okay? Okay, so this is our binary. It says 7.8. So we have our binary point is going to be right here. It might be easier to count from the right side because the fractional bits are 8 bits. So count 8 bits and then put the binary point. Now let's go to the decimal one. In decimal, this is our first bit. It's 0. It means this is Q. This means it's a sign number. So is it a positive or a negative value? Positive, thank you. Both of them are positive. Now, let's look at their integers, okay? The integer of this one is 15, right? the value of these integers. This is 15, this is 16 plus 64. So that's going to be 95. And here we have 64 plus 1, which is 65, dot. Then we go to the fractional one. The fractional one way we said is to calculate it as multiplying by 2 to the power of minus something, right? The first one is minus 1, so this is 0.5, and this is 0. So you see how these two binary numbers in decimal became this. In integer, if these two we were just looking them as integers, you know, there was no point. How much would they be? This one would be 95.5 multiplied to the power of 8, 65 multiplied by 2 to the power of 8. Or you just put this in your calculator simply, right? In your programmer mode, put this binary string and see what's the decimal it is, and it's going to be what you see on the screen. Let me see if I have it here. That was a slide. Yes, so this one is 24,448, and this one is 16,640. So you see how each of these have different meanings, right? Now, we are asked to calculate the summation, right? Let's go the summation of a binary. This one is easiest operation basically in QM in fixed point, because we can look at it as two binaries, they're both positive. Even if they weren't, we didn't care. We're just gonna add them up, right? So 0, 0, 0, 0. Stop me when I make a mistake. Let me separate these. Is that correct? Did I add them correctly? Right? Perfect. Okay. Is that a positive number or a negative number?
It's negative. It's negative.
It's negative, right? If you look at this in Q 7.8, which you would be looking at it, basically, this is your sign bit, right? You have 8 bits here for the fractional one, and this is your integer. So as in the representation of Q 7.8, this is going to be what number? First of all, it's a negative number, so we have to calculate the 2's complement. For the 2's complement, I have to flip all of them. And then add 1. So 0, 0. Correct? And what is this number now? This is exactly that 95 that we calculated on the top. So this is 95. This is 0.5. So this is going to be equal to minus 95.5. What an operation we did, right? So we added 95.5 to 65, and then we got minus 95.5. What just happened? Overflow happened. you added two numbers. Each of them had 7 bits of integer, but the result wouldn't fit in 7 bits of integer. Rule of thumb tells you, right? If even in decimal, when you add two numbers that are 1 digit, right? You add 9 and 2. You would need 2 digits, right? 2 digits to store the summation. So whenever you add two numbers with format Q7.8, ideally what you need is Q.88 to store the results. You need one more bit, basically. Now let's see if we interpreted this. What if we interpreted this as the same integer, but we interpreted it as Q8.8, right? We said, okay, there is a 0 here, actually, because it never got added. And then in that case, this is going to be 0, 1, 0, 1, 0. The same number, right? But this time, we are saying this is the sign, and we have 8 bits of integer. So whatever we got from our summation, it's our integer bits. And here, this is a positive number. And how much is this number? This is 32. And this is 128. So 128 plus 32 dot 0.5, that's 160.5. So if we were interpreting this binary as correctly, thinking that, okay, if I add two integers with 7 bits, the result in general needs 8 bits to store it, and it would consider that, then this result would be okay. But that's not how it works, right? You would store it in a Q7.8, like this one. And then this means this is a wrong result. And what happened was that overflow happened. And when overflow happens, what you do is that you saturate the result. If you want to saturate this result, the maximum you can show with this result is a positive of, with Q7.8 is it's positive, and the rest of them are just 1, the maximum. And this is going to be in hex, this is equal to 7F, F, 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 whatever. And that's your code replace that overflow value with this. So you should check if your result fits within the bounds of a Q7.8 range. You know, we studied the range of Qm.n. If your result fits within that bound, perfect. If it doesn't, if it's positive more, you saturate it to the maximum. If it's less than that, then you saturate it to the minimum. Right? Does it make sense? You're looking at me like it doesn't make sense. Yeah, does it make sense? Yeah, okay. Okay. So this was just addition. Go ahead.
Practically, we're going to cast it, in this case, 2 bytes to then 2 bytes plus 1 bit.
Mm-hmm.
Would it make sense to just cast it to just 3 bytes and just, instead of having 8 there, it'd be better to have,
Yeah, like you're saying instead of 8, you would have 16, for example. No?
50, no? Because you wouldn't include 1 bit inside.
Yes, you can. Yeah, if it's a good practice. Remember with the multiplication, we said last session that always when you're doing multiplication or anything that you know would increase the number of the bits, always store it in something bigger and then bring it back to the standard before doing the next operation. Right? I'll explain it in the next example. How would that happen? So in this one, it says, compute this. Like 0.5 multiplied by 0.25 plus 0.75 multiplied by minus 0.5. This is a great midterm example, for example, right? So, and then it says show all the intermediate steps. So I hope that you don't write 0.25 plus minus 0.35, and this is minus 0.25. This is not what we mean by the intermediate steps, okay? We are going to do the binary version. Okay, let's go with, I'm going to call this the multiplication 1, and then this is multiplication 2. And it says everything is cube 1.15. 1 plus 15, it's 16 bits, so the sign bit is already explicitly included. This one, it means that I have 1 sign bit, 0 integers, 15 fractional bits. Okay, so mentally do this check. Okay, now, when it says cube 1.15 for all of them, it means that every time you multiply, the format has to go back to 1.15. Then, after you add them, then again, everything goes back to 1.15. Okay, that's what you restore. That's what the standard way goes. Okay, so now let's go to 0.5. We're going to decompose M1. This is 0.5, and this is 0.25. And we are showing this in Q1.15. Can somebody tell me in binary what would that be? What is the first bit? Just tell me the first bit. What's that? 0, positive number, right? It's Q1.15. The first thing you put is a sign bit, okay? So for both of these, this is 0. Then, how many integer bits do I have? None. So I'm done. And good thing is that this is 0 as well, so I have 0 here. This is my binary point. Now I have to present the fractional part in 15 bits. 0.5, what is the next bit? 1. Am I done? Everything is 0. Okay, next one. So this is in binary. If you want to do it in hex, this would be 0x4. I say 4 and I write F. 4, 0, 0, 0. Let's go to an integer actually. Let me write the integer too. How much is the integer? Just tell me the formula, not the real number. .5 multiplied by?
0, 1.
0, 1. Yes, in integers though. If you wanted to translate this as a 16-bit integer, how much would that be? Please? 2 to the power of?
15.
Perfect. And that is, if I find it, is 16,384. Okay, next one. We have 0 for the sign bit. Then what is the second bit? 0. What is the third one? 1. Thank you. Then the next bits are just 0. And in hex, this is 0x200. And in integer, that's 0.25 multiplied by 2 to the power of 15, which is 8,192. Now, what we are going to do is multiply these together. Okay? If I multiply a Q1.15 by Q1.15, what is the result? Last session we talked about it. Please? 2.30, yes. The integer bits get added together. The fractional ones get added together as well. Okay, so I have many ways to calculate this. I'm going to go one by one. In binary, we know how to multiply these, right? What we do is that we go row by row, and then we shift it, especially that it's positive, so we don't need to do anything else. And this is covered in binary arithmetic section when we started this first module. Then, okay, I want to do this one as 15. So the binary version, and this one is going to be, this is 134,217,728. And in hex, that's 0, 8, 0, 0, 0, 0, 0, 0. Okay, 8 bytes. And then here, this is the pretty one. So we start. So we have 8 of these because we multiplied 4 bits by 4 bits. 1, 2, 3, 4, 5, 6, 7. Okay. So if you multiply those binaries together by doing like, every bit together, then you would get this number. Now this is, we said, as your friend suggested and said it correctly, we have to know that this is in Q2.30. Okay, this is the result in that. And in decimal, if you want to find the decimal now, I'm going to put the decimal again here. So this is 0.5. This is 0.25. Here, what is the decimal of this one? All I need to do is multiply this by minus 30, which is going to be this one. Or another way is that I put the point here, right? Again, I start from 2 to the power of minus 1, minus 2, minus 3. This is my 0. I have 0 as a sign, and then I have 0 as the integer, and the fractional bits start from here. So in any way you solve this, you would get 0.125. Now, this is the tricky, or the step that sometimes you forget, is that you need to bring this back to the standard form, which is Q1.15, 1.15. Okay, so this is what you're going to do in your code. First, calculate it in a 32 bits. Store your multiplication result in 2.32 bits. Then you would move it to 1.15. How do we do that? If I wanted to go and move this to Q1.15, how would I do that? This one says that keep the sign and integer must be 0, right? What is the sign here in this binary? 0 or positive, right? So I need to keep 0 for this to make sense. then I have 30 bits of fractions, right? I need to only keep 15 of them. Okay, perfect. I'll throw out all of this. I'll throw out all of these ones. I don't need to keep them. So 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, and then 0. This is what is left. If I wanted to convert that 2.30 to 1.15, then I would get to this number, which is 0x 1, 0, 0, 0. Yeah, that's it. And again, if you read that in decimal, again, it's going to be 0.25 in decimal. Any questions? Yes.
Is the hex answer in blue Q2.30 or is it Q1.15?
In this one?
Yes.
This is, you see, like in hex, each of these would translate to 4 bits, and this is 32 bits. So it must be in Q2.30. Everything here is 2.30. We are even looking at this integer as Q2.30. And then to get the decimal value, you multiply by 2 to the power minus 30. Please.
Sorry, so to get it back to the standard form of Q1.15, we just eliminate the extra resolution.
Oh, I just found you. What's your question?
Sorry.
No. Sorry, go ahead.
In order to get it back to the standard form, you eliminate like the extra resolution and the decimal, but how do you compress the integer? Well, using a dot.
That's a good question, and we'll cover it, okay? In this case, it was easy because the integer was already 0,
Right.
and you don't need any bits to store 0, right? But if the integer was 1 and you wanted to keep it as 0, that wouldn't be possible. That would give you error. Go ahead. That's why you always have to keep it at 2.30, then convert it.
Yeah, you can't convert it to like a lower integer.
Yes, if you need more bits to show it, you need more bits, right? Go ahead.
The product, there's two Q1.15s not always give you 0 integer because 2 decimals, like the product is 2 decimals.
That's another way to look at it, yes. If you have 0 dot something, right, then it's always going to be okay. And we'll learn this at the end of this. I will tell you. This is the beauty of using the Q1 point something. It will always make sure that your result is going to fit. Okay, now we just finished the first one. Okay, so this is our M1. Let's quickly do M2 because we have like more slides to go through. M2, 0.75 and minus 0.5. Okay, I need your help to move this quicker. In binary, what is this number? 0.75. What is the first bit? 0. What is the second bit? Third bit? 1. Fourth? What's that? 0. Exactly. This is 0.5 plus 0.25, so easy. Then we have minus 0.5. What is the first bit? 1. Correct. It's negative. Now, what is the second bit? We have to do the 2's complement, right? So we look at this as 0.5 first, and then we calculate the 2's complement. So 0.5 is going to be 0, 1, 0, 0. I don't need the sign bit, so I'm going to write a 0, 0. And this is my point, 0, 0, 0. I have 15 bits to show this. Did I get to 15? No. Right? And then this is my 0.5, and then I do the 2's complement. We flip these, and then we add 1. So that's 0, 0, 0. So this is going to be very similar to minus 0.5, except that you just put a negative. And before you ask, no, that doesn't always work. So it's not always like you put a negative and then consider the, you know, the positive bits. Okay, now if you do this multiplication, which again we covered in the last lecture, and you would do this by hand. So let me just, I'm gonna, like, let's say this is like a little step that we did. Okay, so forget about this one. Now, if you multiply these two, because the second one is negative, you do it row by row, right? You shift it, and then the only thing you have to do is to, on the final row, you do a 2's complement. Okay? And then by doing that, this is what you get. So let's say this is our M2 result. Again, it would be great if you, you know, do this by hand and confirm this result that I'm writing here. It's 1110. Again, this is 32 bits, so how many did I write? 6. And this is in Q 2.1, 2, 3, 4, 5. 5, 6, 7, 8. Yes, this is in Q2.32. So the binary point is here, and it's a negative number. And in hex, this is 1 E8 0 0 0 0. And in integer, that's minus 4002 605.3 184. What else did I have? Oh, and in decimal, again, this is this multiplied by 2 to the power of minus 30. And in decimal, it's going to be minus 0.375. Okay, we are done with the second multiplication. Now, no, we're not done. We have to convert this to Q 1.15, right? So this is in Q 2.30. We go to Q 1.30. No, sorry. 0.15. Okay. In this case, what we do, again, we keep the sign. We have to keep the sign, so it's going to be 0. Oh, sorry. We get 1, and then again, we keep the fractional bits up to 15 bits of it. So 1, 0, 1, 0, 0, 0, 0. And you can see that if you, in hex, this would be 0xd 0, 0, 0. In integer, it's minus 122, 88. And then in decimal, it's minus 0.375. Okay, so this is our M2 result, and then we need to add it to our M1 result. Let's bring M1 from here. Oops. From here. This is our M1 result. Come on, come back. Okay, this is our M1 result. If we add them together, then what we are getting is 0, 0, 0, 0. And this is in Q115 again. if you convert this to decimal, you're going to get minus 0.25. Please.
Hi, the M2 result, you know how you went from 2.30 to 1.15, right? You know how you like dropped an integer bit? Is it always safe to do that? I think someone might have asked this, but I missed it.
Yes, so here, what we have is the first bit is a -1, right? No, it doesn't work all the time, right? What I'm saying, like, you have to know what you're showing. For example, your friend suggested when you're multiplying two Q1.15s, the integer is always 0. Right? The integer is always 0. So if you multiply them, the integer of the result is going to be 0 too. Right? So that's why it's safe to do that. And you can store it, you can show it with 1.15. Go ahead.
So on a midterm, when it says like show all intermediate steps, that means you have to show binary, hex, integer, and
No, no,
decimal.
no. I just showed it to you for... No, all you need to do is the binaries. But you need to show this stage. 2.30 to 1.15. Go.
The integer part was 1, 0, and then the rest of the decimals. It would be the same to do this, right?
What's that?
Like it was instead of 1, 1, it was 1, 0. It wouldn't be safe to drop the 1 this time, right? Because then you would be going to negative.
So the negative, in that case, the negative value would be very large, right? So something must have happened there.
So that'd be like an under. No, like if we were to drop.
You have to keep the sign, and then for the integer one, I don't know if it was 1, 0 something, right, in 2.30, right, and you wanted to show it in 1.30, that's a negative number, but it's very large. Can I like solve this after the class? Yeah, you're good at finding edge cases, so that's why I don't want to say it. Just no. Okay, so everything that we've done so far, I showed it by these steps, right? Kind of like made an algorithm. Like when you want to go from decimal to qm.n, what you would do. And this is examples we solved in the class, okay? So I'm not going to spend too much time on these. You've seen them. It's just like in a good way. And I didn't want to show you this first because I don't want you to just memorize a bunch of steps. Then the same thing for qm.n to decimal. Then here multiplication, we talked about it. Come back. And then here is between Q formats. Again, between the Q formats, when you're upscaling, it's super easy because you keep the sign and you extend the sign, okay? Or if you are increasing the fractional bits, you just add zeros, append zeros to the LSBs. If you're downscaling that, though, you have to be careful because you can't just downscale. Yeah, maybe like for the fractional bits, when you're downscaling, you might lose some, you might have some errors, right? You lose some information. For example, here, when you're going from Q 4.3 to 4.2, that means drop one of the fractional bits. If you drop one of the fractional bits, when you're showing minus 7.375, you would end up with minus 7.25. If you just remove this bit, okay? In that case, what happened? You lose some accuracy. You're introducing some errors, right? So when you're downscaling, you have to remember that even if you're doing that to the fractional bit, you might be losing some information. And downscaling on the integer bit might not be even like you might lose a big chunk of it, right? For example, if you're trying to show 7, the number 7, you need 3 bits just for the integer. You can't show that with 2 bits. The maximum you would show is how much with 2 bits? 3, right? That's the maximum with 2 bits. So you see, like, you have an error of 4 in that case. So, for example, when we are told to show the number 6.615 in Q4 by 4.4. Sorry, when I get stressed, I can't talk properly. So in this case, what we do is that 6.615, we multiply it by 16 in order to convert it to qm.n. And that's going to be 105.84. Then you round it to the nearest integer, that's 106. As soon as you do this, the error happens. As soon as you round up or you round down, you have to round down because that's the closest integer, then that's when the error happens. Then now we can show 106 with 8 bits in this way. And you can say how much error you had. Here we have 0.15% error. What if we wanted to do this with 16 bits? As you can see here, when you multiply it by 2 to the power of 12, you get 27,095.04. When you're rounding down to the nearest integer now, you're only losing 0.04, as opposed to here that you added to 0.16 here. So you see how smaller it got? And again, so you have an error, but the error is only, it got a fourth of the error previously. So now the error percentage is becoming much less. Okay? I don't know how we can lock this so it doesn't distract you. But so one of the other good practices to know is that, okay, if you have to, you know, save space and show some of your results with a smaller number of bits, then how much information you're losing, how much error is being introduced, right? And then this is that you would see. I specifically posted the past midterm examples on your midterm sections. So you can go and see that these are important, you know, topics, because you'll see them in the midterm. Okay. We said, again, one of the errors we have is quantification error, or you're just truncating your result. You're removing some of the fractional bits. The same meaning, it's just an error. It's going to introduce error. And when that happens, then error happens, okay? But it really depends, like how many bits you're losing, how many you're ignoring. For example, one of the ones here is that this is in UQ 4.6, and if you wanted to show it in 3.1, meaning that you're dropping 5 fractional bits and 1 integer bit, then you're getting 7.5, which is like very far away from 8.9375, right? You earn space, but you lose in accuracy. You lose in introducing errors. I will start the next session with division, but I'm just gonna cover this one too. You know, your friend had a very good point. He was like, okay, 1.15, it's right there. You have 1 point for the sign, you have 0 bits for the integer. That means the integer is 0, okay? And that's the case here. I said whenever you see Q 1.15, it's the same as 0.15. So whenever we have either signed or unsigned starting with 0, okay, when the sign bit is implied, sometimes we just show it with the fractional bits. And that means that if it's a positive number, your result is between 0 and 1. And if it's a negative number, it's between minus and 1. What is the benefit of doing that? It's that when you're multiplying stuff, when you're adding stuff, it's always staying in that bound, and you don't have to worry about overflow. That's why for a lot of DSP applications, they use the QX or UQX format. Go ahead.
Is there a difference between like Q0.15 and Q1.15?
Yes. When I say yes, it means that they're the same. Remember, at the beginning of the class, I mentioned that whenever you're only 1 bit away from the standard sizes, which is 8 bits, 16 bits, 32 bits, then assume that the signed bit is implied. Okay? So here, this is exactly as Q1.15 if the signed bit was explicitly mentioned, and this is Q1.31. Anybody else had a question here? Did you have a question?
I was just gonna ask, you said it can't overflow, but it can still underflow, right? Like if it was a long
If
distance.
it's a very, very small number, we get that with the floating point. Yes, yes. That's why we have floating point, in fact. Yeah, that's a very good point. Any other questions? So I just wanted to know you to know this format. And then here, some of the real world applications. Yeah, I don't play these games, but I hope that you relate to them. So the game Doom and PlayStation 1 is the whole thing. Used the Q3.12 or Q.15.16 format. And the good thing is about these is that you'll learn next session that floating point needs a specific hardware. It takes the space. It's it's not fast, but it allows you, as your friend suggested, to store very, very large numbers or very, very small ones, and even special cases that we call them. But you see that a lot of applications like these ones would still prefer to use the fixed points because it is faster, it is cheaper, it will make the circuit smaller. Okay. Then, just before we finish, in Lab 3, we strongly suggest that you try that on your computer, okay, the fixed point and the floating point that you have. Don't load your code on the board and try it on the board. First, try it on your computer, get everything done on the computer, and then go. And yeah, and watch for overflow as we said it. And this is the last note, that in the exams or assignments, you will be told that, even though I mentioned for special cases of standard sizes, you will be told if M includes the sign or not. So don't worry about that part. And then we'll talk about division at the beginning of next session. I don't want to rush through that. Okay? Thank you very much, April.